20 in some databases. So if you're going to do a fingerprint based off this, there's a couple of things that influence it. One is the rate of the access point. Clearly, if you can transmit packets faster, then the numbers for duration are going to be smaller. And over time, 802.11's picked up a couple of optimizations, short slot time and a short preamble. And if you wanted to have a perfect fingerprint, you would take every 802.11 implementation, vary every one of these fields, so run it against this speed, short slot time, no short slot time, short preamble. But in reality, some of these don't make sense. You would rarely see an 11G network running with no optimizations. So I have 4 databases built, which seems to be working pretty well. I'll probably make some more. Okay, so now I'm going to give you just show you guys what's in a sample fingerprint file. So this example comes from an Atheros card, and in my opinion, Atheros cards are well behaved because they don't do anything crazy. And you just see here, the 314 value next to association request is just duration value 314 shows up 100% of the time in association requests. And the probe requests, it's 0 97% of the time and 314 3% of the time. And that's a kind of strange thing. Why would the values change 3% of the time? I have no idea, but it kind of makes the card stick out. And similarly for authentication in data and other fields. And the other probabilities it computes is the probability of seeing a duration regardless of the packet type. So down at the bottom, see a 0 with 19%. That means duration value 0 is used 19% of the time, regardless of the packet. And so those probabilities at the bottom are actually going to be dominated by the value used in most data packets because the vast majority of data sent is data packets. But they come into play later. So here's an example of Prism fingerprint. It's poorly behaved. So the biggest difference here is that the authentication packet you see there has a value of 53389 100% of the time. Now, it's a lot of microseconds for something that doesn't get acknowledged, or maybe it does. But anyway, that's a very long time. In fact, it's so long that it's illegal. Any number larger than 32767, the standard says to just ignore. So Prism cards put 2 illegal values in here, one in authentication, one in null function. So they stand out really easily. They do some other weird things too, but don't have time to get into it. And you can see that they use more data. There's 3 distinct data points in here for the data packet, and on Atheros there's only 2. So not only do they use different ones, but they use more. And so I want to give you guys a real demo in a second, but this is just so I don't have to jump out of PowerPoint all the time. If you were to run a program to try to take an input PCAP, one came from an Atheros card, and the packet comes from, or the PCAP comes from an Atheros card on the left. Say, okay, it's an input PCAP. I'm only going to give you 2 fingerprints to compare it to, an Atheros card or a Prism card. And you can see right here that if I just gave 2 people in the room, or a person these 2 fingerprints in a packet capture, they could go, oh, this is a Prism card because it's got this awkward duration value. So it's no magic here that this program can tell between a Prism and a Atheros. It gets trickier when you throw in 14 or 15 cards, all who are much more similar. So the score here for the left-hand column is says, okay, it's an Atheros card, I think 51.4, and if it's not, then I guess it's a Prism. Those numbers aren't actually probabilities, they're just scores. You can't interpret them as probability, it's just ordered. And similarly, on the right-hand column, it's okay, got a Prism PCAP. I only got these 2 fingerprints to compare it to. What do you think it is? Oh, it stands out like a Prism card, much more distinctly because it's got all those crazy unique values. So, a realistic example is here. You say, okay, got a PCAP file. The MAC address I'm interested in is 00AA95, etc. And I want to know what kind of card it is. And so now it's comparing it against my entire database of 14. And it's probably hard to read, but the first row right here says Broadcom Mini PCI. That's not a Broadcom Mini PCI. This is actually my PowerBook. And right underneath it is Apple Airport Extreme. But so it was wrong in a sense, right? The wrong chipset is on top, or the wrong driver is on top. But the scores are very close here. The score for the Broadcom Mini PCI is 79, and score for the Airport Extreme is 78. So it had a hard time telling them apart. But the interesting thing is all the chipsets on top are Broadcom. And then the rest of them seem to clump together too. Further down below, the Atheros are all next to each other. So you can see that it's really picking up how these chipsets are related. And so, all right, I'm gonna try to type and talk, so hopefully my mic doesn't get too annoyed at me. I think it will though. Right. Okay, so this is just the example I just showed in the PowerPoint where I'm trying to fingerprint the Apple Airport card, so you can see the program actually run and not just a bunch of PowerPoint slides. So a more interesting example would be, let's say you want to know if somebody's got a vulnerable, this isn't going to work so well, a vulnerable Centrino driver or the new one, and I quick downloaded their 130 meg zip file to patch my driver. I think operating systems are smaller than that in some cases. So I looked and looked. I thought, surely this is extra junk and I can just find the driver. It's 130 megs. So I got their new driver and I attempted to fingerprint it, and I can actually distinguish it from the older one. So I'm gonna have to just mute my mic for a second, otherwise you guys can get an earful of feedback and type something, so hang on.
While he's typing, can I ask a question? How many people here are running wireless sniffers right now? Can you just raise your hand? No, nobody? One? Somehow I feel the actual number is much higher than the reflected number in my survey. Just wondering.
Okay, so the command I just awkwardly typed says, I got a PCAP. This is one I took earlier because I didn't know if anybody was going to be messing with my wireless network, and I wanted to make sure this worked, though I will be doing a real demo later. So I got a PCAP. This is from a vulnerable Intel driver, and I'm just going to try to match it against my database. And you can see up on top are two Intel drivers. sys-vuln 9039 is the name I gave the vulnerable driver, and that was a vulnerable PCAP, so that's good. Let's try this, the patched updated one. And you see the patched one comes out on top. So in between fixing, the remote code execution issues, they've also changed the behavior of the driver, intentionally or not. Maybe there was other, fixes besides security. So you can actually tell these apart, which would be, great if you're trying to actually exploit someone, right? So that's just to show you an example of this. Now, back to the slide. So if you wanted to measure the performance of one of these algorithms, it's a good question as to how would you do it. Measuring it against a single database is pretty easy, right? If you had a bunch of PCAPs, was it right, was it wrong? Well, that's easy. But if you've actually got a bunch of different databases, because you need more than one, you can't just have a B one, you want to have a G one, and so on. They might be different size. For example, I've got a G-only database. It's only got 7 cards I think in it because all my B1s can't connect. And so if you just wanted to measure the errors per database, it's not comparable. It's a lot easier to get it right when you only got 7 versus 14. So the way I decided to measure the performance of this tool is just how much better does it do than random on a given database, and that becomes comparable across databases. So in this case, if you assume random's just going to throw things around, the right card is going to end up somewhere in the middle of the list, and you're going to see a whole bunch of, I should have explained the table first, huh? Okay, so S1, S2, and S3 refer to 3 distinct PCAPs I've taken for a given implementation. And the zeros and the ones in here and the 2's represent how far down the corrected device driver was found. So for example, that airport that I showed you a minute ago, this one where the airport card is 1 down in the list, that corresponds to, PowerPoint hating me, no, corresponds to the 5 row, because that's the airport card, and the 1 in bold right there. So it was 1 down, it gets a 1. All the zeros mean it did perfect on all those input P caps, and 2 means it was 2 down. And you can see there's an awful lot of zeros here, which means you're doing pretty good. In fact, you can tell exactly how well you're doing. You're doing 30 times better than random. Because random would just, it'd end up in the middle roughly, and so you see a bunch of 6s everywhere on average, so you can compute how many times better you're doing. So 30 times better than random is, I think, pretty good. I mean, people didn't think you could do this before. They definitely didn't think you could get past the chipset. It looks like there's a lot of device driver versions in here. And should I point out that the top 4 rows on this are all Atheros cards. The IDs number 2, 3, and 4 are exactly the same driver. They're different cards with different chipsets, but it's the exact same bit-for-bit driver. So you can tell when you swap out a different card using the same driver, you can tell it's apart most of the time. So how's it work? Do we have time to say how it works? Guess so. Oh, okay. So how's it work? I'm only going to talk about one algorithm, simple compare. Simple compare treats the fingerprint as 2 sets of duration values. So ignore the packet type here, and you take the intersection of these sets. For every 2 points that are in the intersection, you return 1 minus, and then some math. You take the number of packets with the same duration, divide by the number of packets. So that's just the probability of seeing that duration on the card on the left, minus the probability of seeing that duration of the card on the right. And the idea here is if these 2 cards use the same duration value, but in totally different scenarios, one uses it all the time, one uses it, almost another time, this is actually going to be close to 0. It's going to be 1 minus a lot. But if they're using the duration in roughly the same proportion, then it's going to be close to 1. So the higher the score, the better it does. And if you just do this, if you just look at the durations and you ignore packet types, you get to do 10 times better than average, which is good. You'll at least get chipset level resolution. If you then simple compare says, okay, we're going to take the packet type and the durations into concern, and then we compute the probability of seeing the same packet type duration. So you take the packet types into account. You do 21 times better than random. Now that's a lot better. And if you actually were to combine these, which is what simple compare does, you get 23 times better than random on average across a lot of samples across 4 databases. You can see, some of these do better than others. There's a 46.8 in Lexi, and in some other algorithms that gets even higher. But on average, across a lot of databases, 23. So that's pretty good. Okay. So before we go do the video, I'm just going to show you a quick live demo of the fingerprinting stuff. Okay, so all those zeros on the screen mean I'm trying to match it against this laptop right here, and it doesn't have any packets for it because this card is off. So you can know that this is actually happening in real time. The packets are being captured with Kismac. I'm gonna hope this all works out, huh? Turn on my wireless card. Okay, good. It's connecting to the access point. I hope that works. Okay, so